All right. 7.2. More equations. Solving 7.2, solving equations again. Okay, so let's glance back at 7.1. We had things like natural log of x minus 1 equals 3, where the first thing you do is you unwrap the function. Step 1, unwrap the log function by doing the natural exponential base. Those cancel. X minus 1 equals e to the 3. So now all we're going to do in 7.2 is we're going to say your first step is not to unwrap the function. Your first step is isolate the function. So instead of natural log of x minus 1 equals 3, maybe I have 1/2 times natural log of x minus 1 equals 3. So I don't just do the exponential. First, I have to isolate the function. So I'll multiply both sides by 2. And I get natural log of x minus 1 equals 6. And then I just keep going forward after that. So it's one more piece of things that you have to do. All right. Let's see, are there more examples? Let's just do some more examples. So -3 equals e to the 2x plus 1 minus 5. And you might say, wait a minute, an exponential can never get me a negative, but we haven't isolated the exponential yet. So first I add 5 to both sides and I get 2 on the left side, and that's okay because I can get 2 out of an exponential function. Natural log of 2 equals natural log of e to the 2x plus 1. Those cancel, so that's just 2x plus 1. Natural log of 2 minus 1 equals 2x, and natural log of 2 minus 1 all over 2 equals x, and I'm done. Let's see. Maybe I have -7 equals minus 3 square roots of x plus 4 plus 2. And I say, wait a minute, a square root shouldn't be able to get me a negative number, but I haven't isolated the square root yet. So first I have to isolate it. Again, this is just solving for x. You've done this a number of times. Now we're just giving it some fancy words. And I get 3 equals the square root of x, the quantity x plus 4. I check and I ask myself, is this going to give me a valid answer? Yes, I can get a positive out of a square root. So I square both sides, those cancel, and I get 9 equals x plus 4 and x equals 5, and I'm done. Right, and you still have to be careful because maybe I get something like 8 equals -2 square root of x minus 1 minus 4. Sure. And I'll add 4 to both sides. I get 12 equals -2 square root of x minus 1. Divide both sides by -2. And I get -6 equals the square root of x minus 1. And so I square it because I'm not stopping and I'm thinking because I'm just doing the algebra. And I don't stop to think, hold on, I can't get a negative out of a square root. So you do need to stop. Once you isolate the square root, you need to stop and think through, can I get an x that will make this equation true? But rather than just charging forward, which I did on purpose, stop once you've isolated the function and ask yourself, is there an x that can make this equation true given my function? There is not. There's no way to get a -6 out of a square root function, so there's no solution. And if I tried to do it, I would find a false solution. All right. I just feel like these are more the same. All right, so 2 ways to solve log equations. This is page 170. So suppose I have something like 1/3 log base 10 of x plus 2 equals 1. So option 1, isolate the log. This is how I always do it. So first I'm going to multiply by 3. And I get log base 10 of x plus 2 equals 3. And then step 2 is exponentiate both sides. I get 10 raised to the log base 10 of x plus 2 equals 10 cubed. 10 to the log base 10 cancels, and I get x plus 2 equals 1,000, and x equals 998, and I'm done. The other way to approach it, if I have the same, is to start with the exponential, which I suppose you can do. I don't know why you would. Oh, that shouldn't be a, that should be a 1. 10 to the 1. Let me rewrite this. 1/3 log of x plus 2 equals 1. That's the same equation. So I'll start with the exponential. 10 to the first is just 10. 10 to the 1/3 log of x plus 2. I can rewrite using my rules of exponents as 10 to the 1/3, or 10 to the log base of x plus 2, then all raised to the 1/3. These cancel, and I get x plus 2 to the 1/3 equals 10. And how do I get rid of the 1/3? I need to raise both sides to the power of 3. And I get to 998 again. So yeah, you can do it this way. I never do it this way. I just isolate the log first. There are some times when maybe things turn out a little bit simpler if you do it one way instead of the other way. But either way works. I'll do one more. This time I'll do 3 plus natural log of x minus 4 equals 17. So option 1, isolate the log. So I get natural log of x minus 4 equals 14. If I exponentiate both sides, those cancel, and I get x minus 4 equals e to the 14th. So x equals e to the 14th plus 4. That's the number, and so I'm done. The other way is to exponentiate first. So I have 3 plus natural log of x minus 4 equals 17. So exponentiate both of those first. And now use your rules of exponents to say, if I have e to the 3 plus, that's e cubed times e to the natural log of x minus 4 equals e to the 17. And now this is a number, so I'll divide both sides by that. Those cancel. E to the 17 divided by e to the 3rd is e to the 14, and I'm right back here. And then those cancel, and I get x minus 4 equals e to the 14. x equals e to the 14th plus 4. I don't know why anyone would do it this way, but some people do, and that's fine. Isolate the log, then exponentiate, much easier. All right. Let's see, f of x equals x minus 3 squared minus 10. This is kind of like question 4. So I could, if I wanted to, I could draw this. This right here is in vertex form or max min form. Since that's a positive coefficient, that must be the minimum. The minimum is -10 and it curves when x is 3. And positive leading coefficient goes up like this. And maybe I have 2 roots, but I don't know what they are yet, although I could figure out how to factor this and get it into factored form. So if I were to solve f of x equals -3, there's -3 right there. You notice there are 2 points where my function equals -3. So I should have 2 solutions. -3 equals x minus 3 squared minus 10. Add 10 to both sides, isolate the function, and I get 7 equals x minus 3 quantity squared. Get rid of the square, I'm going to do the reciprocal, or in this case, the square root. So square root of 7 equals x minus 3. So x equals 3 plus the square root of 7. And hold on, that's weird. I only got 1 solution here, but my graph says there should be 2 solutions. So where did I go wrong? I went wrong right here. Because if 7 is x minus 3 squared, what are the numbers that when I square give me 7? Well, square root of 7 is one of them, but the other one is the negative square root of 7. So if I square the negative square roots of 7, that gives me a positive 7. So 3 minus the square root of 7 is my other x value. So you have to be careful when solving, especially any kind of quadratic. We know quadratics frequently have 2 solutions, right? Because they go up on both sides of the vertex. There's only one place where a quadratic has a single solution, and that's right there. Everywhere else that it has any solutions, it has 2 solutions. So you have to be careful when solving to remember that undoing a square gives you both the positive square root and the negative square root. Let's use our same function and do it again. F of x equals a quantity x minus 3 squared minus 10. And I'm going to solve f of x equals 2. Okay, so 2 equals x minus 3 squared minus 10. Isolate the squared term, add 10 to both sides. 12 equals x minus 3 squared. So how many numbers, when I square them, give me 12? There are 2. There's the square root of 12, and there's the negative square roots of 12. Those are both numbers that when I square give me 12. And so I get 3 plus the square root of 12 and 3 minus the square root of 12 as my x values. Okay, how about f of x equals minus 20? Negative 20 equals x minus 3 squared minus 10. Add 10 to both sides. I get negative 10 equals x minus 3 squared. And maybe I stop and I ask myself, if I'm squaring something and I possibly get a negative number, I cannot, so there should be no solutions. And if I go one step further and I do square root of negative 10 equals x minus 3, right, that's not possible. There's no solutions. And if I flip back over at my graph and I say, when does my graph touch negative 20? It never does. So that's another reason to know that there are no solutions. All right, moving on. What if you have an equation that's what's called a mixed, I don't know if it's what's called mixed radicals. So let's look at, for example, the square root of 4x minus 2 equals 5x. And I'm trying to solve this for x. So there's a couple of things you could try. There's only one thing that's really a good idea. And the good idea is to isolate the radical. As step one, we're already in a form where the radical is isolated. And step two is undo the radical. I'm saying the radical instead of the square root because that could be a cube root or fifth root or fourth root. And in this case, we undo it by squaring it. So I have square root of 4x minus 2 equals 5x. I'm going to square both sides. On the left side, I have 4x minus 2. On the right side, I have 5x. Quantity squared, which is 25x squared. And I've gone from a mixed radicals equation to now an equation with an x squared and an x and a constant, which I could rewrite by subtracting, well, I'll rewrite by subtracting the minus 4x and adding 2. And I end up with a quadratic equation, which I can now solve using the quadratic formula or by factoring if it's simple. This one is not simple. The one in your workbook probably is, but I just made this one up. If I do want to solve this, I can just jump straight to the quadratic formula, which is minus b plus or minus a square root of b squared minus 4ac. Oops. Let me write that again. Minus b plus or minus a square root of b squared minus 4ac all over 2a. B is negative 4. So minus b is positive 4. That's 16. Minus 4 times a, which is 25, times c, which is 2. All over 50. So that's 4 plus or minus 16 minus 200 is don't really want to start this whole video over. So just hang with me while I demonstrate what's going on with this equation. Not exactly the one that I wish I had picked, but I'm making it work. So that's 16 minus 200, which is negative 184 over 50. And at this point, you should say, I can't take the square root of a radical, so there are no solutions. Now, I didn't know that until I got to this point, but once I'm at this point, I can kind of visualize what this function is going to look like. 5x looks like this. Square root of 4x minus 2 looks like this. And at no place do these two functions touch. So there are no x values that make them equal. So there is no solution to this equation. So as far as you watching this video, not super helpful. I get that. Let's do a different one. I'm gonna pause and think of one that'll work. Okay, I think I got one. Let's say we have the mixed radical equation 4x minus 3 under a square root plus 10 equals x. All All right, so step one is to isolate the radicals. So let's subtract 10 from both sides. And we get square root of 4x minus 3 equals x minus 10. The next step is to square both sides. And by now you should recognize whenever you square, you should think about warning possible false solution. So you need to double check once you get an answer. Anytime you square a radical, you may be introducing a possible false solution. Or, as we saw with the other ones, you may end up with two solutions. So squaring basically means slow down and check your work. So if I do that, I get 4x minus 3 equals, I'm going to go ahead and multiply this out, x squared minus 20x plus 100. And I've turned it from a mixed radical equation into something with just x squareds and x's. So if I subtract these over, I get x squared minus 24x plus 103 should equal 0. And I can use my quadratic formula on that. Minus b plus or minus the square root of b squared, 24 squared, minus 4 times a, which is 1, times c, which is 103, all divided by 2a. 24 squared is much bigger than 412, so this is going to give me a number. Let me pause while I figure that out. All right, generally, I say leave things as radicals, but I do want to demonstrate this piece of it. And I think that'll be easier if we have decimals. So when I did this, I got it was approximately 12.8. So that's divided by 2. And so that's going to be 36.8 over 2, which is 18.4. And if I subtract it, that's going to be 11.2 over 2, which is 5.6. So that's what I think are my two answers that make this true. But I squared it. So warning possible false solution. I need to check both of these. And the easiest way to check is just plug them in. 4 times 18.4 minus 3 under the square root plus 10. I asked, does that equal 18.4? And it'll be approximate because I got a decimal. 4 times 18.4 is a little bit more than 72. Let's say 75. So that's, in the end, it's the square root of 72, which is, square root of 72 is approximately 8.4, which when I add to 10 gets me 18.4. Notice I'm taking the square root of a positive number, so that's okay. If I try the other one, I get 4 times 5.6 minus 3 under the square root plus 10. I want to know, does that equal 18.4? Well, 4 times 5.6 is about 22. Um, 22 minus 3 is 19. Square root of 19 plus 10. And the square root of 19 is somewhere between 4 and 5. Let's say it's 4.6. And it is not equal to 18.4. So I generated a false solution. This is a false solution. The reason I generated a false solution is I squared a radical. And when you square a radical, you generate two branches of reality, if you want to think about it that way. It's like a multiverse. Just popped into my head, right? If any of you have seen Loki, when you square a radical, you get a Loki variant. And that Loki variant needs to be pruned. Yeah, I went way too deep there. Moving on. How about if you have an equation with mixed logs? So you could have, oh, now I see why you might need to raise things to an exponential first. let's do natural log of x plus 3 minus 4 equals natural log of, oh yeah, no, you don't need to do that. Natural log of, let's just do 2x. Okay. First thing to do is to isolate all of the logs. So to do that, I'm going to subtract natural log of 2x from this side. And I get natural log of x plus 3 minus natural log of 2x. And then I'm going to add 4 equals 4. And now I can use my log rules to say, oh, I've subtracted 2 logs. That's the same thing as dividing inside the log. And I'm thinking this may not be an example I want to do because, nope, I don't want to do this example. I came up with it off the top of my head and it's not one that we should do, and that's okay. Let me do a slightly different one. So erase that from your memory. Let's do log base 10 of x minus 2 plus 3 equals negative log base 10 of x minus 1. Let's do that. So still isolate the logs, but this time I get to add those logs, and that's going to make everything a lot easier. Oops, except it's a negative 3. If I bring them all into a single log, then I ask you, can I ever take the log of something and get a negative number? Oh yeah, that I can. That's fine. I always get these confused. Yes, I can do that. I can take the log of something and get a negative number. I just can't take the log of a negative number. All right, so now that I've done this, this is log base 10. I can raise everything to the 10, or put everything in the exponent of 10, and those cancel. And I get x minus 2 times x minus 1 equals 10 to the minus 3, which is 1 over 1,000. And I've gone from a logs equation to what ends up being a quadratic equation. If I multiply this out, I get x squared minus 2x minus x plus 2. And then I'll subtract that 1 over 1,000. So I get x squared minus 3x plus 2 minus 1 over 1,000 equals 0. And now I can use a quadratic formula to solve for x. Okay, this is another one that's not working out. I think I can cut it from the video, but if I can't, just cut it from your brain instead. We'll prune that along with the Loki variant. So let me try it again. I paused the video. I took a little bit of time. I thought of an equation that is going to work the way I want it to. So let's consider log base 2 of x minus 3 equals 1 minus log base 2 of x minus 2. So again, we isolate the logs. Plus log base 2 of x minus 2 equals 1. Using our log rules, we can combine those into log base 2 of x minus 3 times x minus 2 equals 1. Since it's a log base 2, if I put them both in the exponent on 2, those cancel, and I get x minus 3 times x minus 2 equals 2 to the first, which is 2. And I've turned a log equation into a quadratic. And once again, since I have a quadratic, be aware of, how about beware? Beware of false solutions. Now I feel like I should re-record this and just call them variants. But not all of you have watched Loki, so that's probably better that I don't. Beware of false solutions because we had a quadratic now. But let's go ahead and solve this and then we'll check. So if I multiply this out, I get x squared minus 5x plus 6 equals 2. Subtract 2 from both sides. I get a nice quadratic equation, which this time I made sure I set up carefully to be easily factorable into x minus 1 times x minus 4. So x could be 1 or x could be 4. But we have to check because we are wary of false solutions. Whenever you have a quadratic and you're squaring things, you turn things from negative to positive. And remember, turning things from negative to positive is risky when you're working with radicals and when you're working with logs. So to check, we just plug it back into our original. So let's check x equals 1, log base 2 of 1 minus 3. I've already seen a problem. Equals log base 2 of 1 minus 2. That's log base 2 of negative 2 equals 1 minus log base 2 of negative 1, but we can't have negative numbers going into logs. So x equals 1 is a false solution. It is a Loki variant. And I'll check my next one. Log base 2 of 4 minus 3 equals 1 minus log base 2 of 4 minus 2. This is better. Log base 2 of 1 is 0. So that's okay. And then I have 1 minus log base 2 of 2, which is 1 minus 1, which is 0. So that's okay. So that's my solution. So the lesson here is, especially when you have quadratics, beware of false solutions. And in general, just always check your answer. You get an answer, you get 2 answers, you get 2 answers, or 10 answers, check all of them. End of video.